picture. Let me just share my slides. Okay, I'm now sharing my slides. So I hope everyone can see them. Okay, I just took the slides from your book. Okay. Um, Again, please, um, I would like to apologize for my voice as I'm having a cold as of the moment. Okay, I'm not feeling well. Okay, so please bear with me. Okay, so for tonight, let's try to discuss compressibility of soils. Okay, now when we try to assess the bearing capacities or the soil bearing capacities in the ground, one of the criteria that we consider is the settlement criteria. Okay. Now, depending on the structure, we can specify different settlement criteria, depending also on the type of foundation. Okay. Normally, we specify, say, 25 or 50 millimeter settlement criteria. Okay. Sometimes the designer would also specify the settlement criteria. Okay. For example, in overhead transmission line structures, the designer can have settlement criteria as much as uh, 300 to 500 millimeters. Okay, that's already about half a meter. Okay, because the structure is not so sensitive with respect to settlement. The only concern is with respect to the cables, no? The transmission cables, which can tolerate as uh, as deep as 500 millimeters of settlement. Okay, so it depends. No? It depends on the structure that you're dealing with. Okay, um, I I also prepare reports for OHTL structures, geotechnical reports. So that's why I got to familiarize also with the settlement criteria specified by structural engineers. Okay. Now, in assessing the settlement, um, normally we consider two basic types of settlements. Okay. This is the one you are seeing here now in this slide. Okay. Now, in actual practice, aside from this, because these settlements are considered as static settlements, okay, in actual work, we also consider dynamic settlements. That's actually under the uh, principles of soil dynamics, wherein we try to consider also liquefaction settlement, where liquefaction is a behavior of some types of soils where it tries to liquefy. It acts like a liquid during an earthquake. Okay, depending on the magnitude of the earthquake. Okay, and also depending on the groundwater levels. Okay, so when we prepare geotechnical reports in the determination of the soil bearing capacity needed by structural engineers for them to design the foundations, okay, um, we try to provide the bearing capacities based on shear failure criterion as well as this one here, the settlement criteria. Okay. For the moment, we will not be discussing liquefaction settlement. That's under the subject on principles of soil dynamics. Okay, but as of the moment, let's try to discuss only the static settlements. Okay. Okay. So to begin with, so with respect to static settlements, so we have now this one here. Okay. So yeah, so settlements can also be treated as compressibility, no, of soils. Okay. So soils can compress. Okay. So the effect of this compressibility is now the settlement. Okay. And this compressibility is caused by a stress increase. Okay. As I think last meeting we have discussed in situ stresses. So these are the natural stresses in the ground, in situ stresses caused by the overburdened pressure. Okay. By the weight of the soils themselves. Okay. But in addition to that, um, for soils to settle, okay, we need to add the stress. No? Okay, there will be a stress increase caused by structural foundations. Okay, dead loads, live loads, and so on and so forth. Okay, so a stress increase caused by the construction of foundations, okay, or other loads tend to compress the soil layers. Okay, I think by next year or maybe this year, you already have some probably some basic structural design wherein you try to design shallow foundations. Okay, say maybe for a few stories. Okay, 3, 4 stories or six-story buildings. And with that, you try to design the shallow foundation. Okay, so that shallow foundation it will create a bearing pressure, a structural bearing pressure, which can cause a stress increase into the ground. Okay, and this stress increase will now create this settlement into the ground. Okay? So let us now try to understand these basic settlements. Okay? So this compression of the soils is caused by a deformation, okay, of the soil particles. Okay, so the soil particles can deform, or the relocations of soil particles. Okay, the soil particles themselves displaces from each other. Okay, or if there is an expulsion of water or air from the void spaces. Okay. So with that, we now have here these three basic settlements. Okay. Basically, there's only two. We have the elastic settlement or the immediate settlement. And then we also have the consolidation settlement, wherein the consolidation settlement is composed of a primary and secondary consolidation settlement. Now, for the first one, when we say elastic settlement, or this is also called immediate settlement, okay? Now, this settlement is caused by the elastic deformation of a dry soil or of a moist or saturated source. Okay. Without, take note, without any change in the moisture content. Okay. Now, these elastic settlement calculations are generally based on equations derived from the theory of elasticity. Okay. The theory that you learned in strength of materials, for example. Okay. Now, the other types of settlement is the consolidation settlement. Okay. Now, for consolidation settlement, again, there are two types. You have the primary and the secondary consolidation settlement. Okay. Wherein these three types of settlements, we will have some formulas for them later on. Okay. Now, the primary consolidation settlement is basically the result of a volume change in, take note, this is in saturated cohesive soils. That means it is below the groundwater level, okay? In saturated cohesive soils, due to the expulsion of the water that occupies the void spaces, okay? So water is being expelled, no? Out of the void spaces in your soil matrix. Okay. Now, the secondary consolidation settlement, this is observed in saturated cohesive soils as well as organic soils, and basically it's the result of the plastic adjustment of soil fabrics. No? Okay, so there is some movement, no, in the soil fabrics. No? Um, Take note here, it mentioned cohesive soils. Okay? So again, when we say cohesive soils, these are normally, yeah, mostly the clay, huh? The clay soils. Okay, clay soils. Okay? Then with respect to consolidation settlement behavior, okay, then yeah, it's mostly on clay soils. Okay. Now, when you say granular or cohesionless soils, okay, then we have the gravels and the sands, no? Yeah, which can encounter immediate settlements. Okay. Okay. So now for the total settlement, okay. So the total settlement can now be defined as the sum of these three settlements, which is now the sum of the primary consolidation settlement, okay, the secondary consolidation settlement, okay, and the elastic settlement or the immediate settlement. Okay, in practice, normally we call it immediate settlement. Okay, because the effect is immediate. Okay, and then also in actual practice, we also add here plus the settlement due to liquefaction. Okay, yeah. So there are basically four basic terms. Depending on the type of soil material you will encounter during the geotechnical investigation. Now, when foundations are constructed on very compressible clays, the consolidation settlement can be several times greater than the elastic settlement, which is quite true, no? Based on our experience as well. No? So, what Professor Das mentioned here in his book is also true based on what we have experienced when we prepare geotechnical reports. Okay. Now, okay. So, out of these three settlements, let's first discuss the elastic or the immediate settlement of foundations. That's the SRE, which basically occurs directly after the application of a load without a change in the moisture content of the soil. Okay? Now, the magnitude of the contact settlement will depend on the flexibility of the foundation, okay, whether you have a rigid or an elastic foundation, as well as the type of material on which it is resting. Okay, yeah. So take note here, the effect is immediate, no? Without a change in the moisture content of the soil. Okay, let's go back to this figure in a while. Okay, so that figure, okay, the figure 11.3 in your book as well. Okay. If you have your book, okay, you can just go to this figure also. Okay. If the screen is not clear with you, okay. So that figure shows a shallow foundation which is subjected to a net force per unit area, okay, equal to delta sigma. Okay. So then we let the Poisson's ratio and the modulus of elasticity of the soil supporting that foundation to be symbolized by mu sub s and then E sub s respectively. Okay. So if we go back to this figure now, okay. So we now have here a shallow foundation. Okay. This can be an isolated footing which you will be designing later on when you will be in your last year, I think, okay, or maybe next semester. Okay. So then you will be calculating and a load. No? Okay, so this one here. No? So you will be calculating a net force, okay, um, due to the foundation. Okay, so you have here a net pressure, okay, okay, or a bearing pressure imposed by the shallow foundation. Okay. Now again, depending on the foundation type, you can have a rigid foundation settlement, which is this diagram here. Okay, you have a rigid foundation settlement, or you can have a flexible foundation settlement. Okay. Yeah. So the foundation can have a dimension of B times L, where B is the width. Okay, and then L is the length of the foundation. So if you have a square foundation, then the width and sorry, if you can see my cursor, the width and the length are just equal. Okay. Then aside from that, you also have the depth of the embedment. Okay, or that's D sub F, or the depth of embedment of the foundation. That's your F. Okay, the depth of embedment. That's measured from the ground surface, okay, down to the bottom of your foundation. Okay. Then from the bottom of the foundation down to the soil rock interface, okay, the soil rock interface that can be considered as depth H. Okay. And then the soils below the shallow foundation can have these properties here, which we need to compute for the elastic settlement or the immediate settlement. Okay, so we need to know these properties depending on the type of the soil. Okay, may it be sands, gravels, or silts or clays, no? For example. Okay, now theoretically, if the foundation is perfectly flexible, okay, so this one here, okay, so it follows this behavior when it settles, okay, flexible foundation, okay. So theoretically, if the foundation is perfectly flexible, then the elastic or the immediate settlement may be expressed by this equation here, okay, wherein Uh, delta sigma here is the net applied pressure on the foundation. Okay. Sorry if you're seeing my cursor. So that's the net applied pressure on the foundation, which is actually this one here. Yeah? Okay. The pressure imposed by the foundation. Okay. And then mu sub s is the Poisson's ratio. That's this one here. Then E sub S is the average modulus of elasticity of the soil under the foundation, measured from Z equal to 0 to about Z equal to 5B, or 5 times the width of the foundation. Okay. So depending on the evaluator, yeah, you can sometimes consider 2B or 3B or 5B. No? Okay, it depends. No? Okay. Then B prime here is actually B over 2 if you are checking for the settlement at the center of the foundation. And then B prime will be equal to the B or the width of the foundation if you are trying to measure or calculate the settlement at the corner of the foundation. Okay. And then you have here I sub s, which is the shape factor. Okay. This I sub s is equal to this formula here. Um, so that's equal to this formula um, f sub 1 plus this term here with respect to mu sub s times f sub 2. Okay. Where f sub 1 is equal to this formula here as a function of a sub 0 and a sub 1. Okay. And then f sub 2 here is a function of a sub 2 and n prime. Okay. Now, a sub 0 is given by this formula here. Okay, so this a sub 0 is given by this formula, which is a function of m prime and n prime, which will give the formula later. Okay, okay, and then a sub 1 is given by this formula here, which is again a function of m prime and n prime. Okay. And then you have also here a sub 2, which is again a function of m prime and n prime. Okay. So later on, we'll have these values for the m prime and n prime. Okay. So what else? So we have now a sub 0, a sub 1, and a sub 2. Okay. Okay. So that's to get I sub s. So we now get this one. Okay. Then we also have I sub f. Okay. I sub f is the depth factor. Okay, depth factor, which is a function of the embedment depth of the foundation over the width of the foundation, and then also the ratio of the length of the foundation over the width of the foundation, as well as the Poisson's ratio of the soil material. Okay, so that's your I sub f. Okay. And then lastly, you have here your alpha. Okay. So alpha is a factor that depends on the location on the foundation where the settlement is being calculated. Whether you are calculating at the center of the foundation or whether you are calculating at the corner of the foundation. Okay. So in the case wherein we are calculating at the for the settlement, no, the elastic or the immediate settlement at the center of the foundation. Okay, so that's basically here. No? That's at the center of the foundation. This is at the corner of the foundation. Okay, so at the center of the foundation, then alpha can be equal to 4. Okay, and then m prime is equal to L over B. Okay, this is the length of the foundation over the width of the foundation. Okay, if it is square, then this is just one. No? If you have a square foundation, okay, then m prime is equal to h over b over 2, or 1/2 of the width of the foundation. And then h is okay. If you go back to the figure, this is now your h. No? Okay, it is actually the depth or the distance from the bottom of the foundation down to the soil rock interface or down to the competent material. No, we can call this the competent material. Okay. Okay. Now, if you're calculating the settlement at the corner of the foundation, then alpha is equal to 1. Then m prime is just the same. Okay, that's the length of the foundation over the width of the foundation. Then n prime is equal to h over b. Okay. Yeah. So you have here take note b over 2 and b, no, which is just the same for b prime. No? B prime. No? Okay. So we have b over 2 at the center of the foundation, then b at the corner of the foundation. Depending on which part of the foundation you are trying to calculate for the settlement. Okay. So just to go back to the equation. So again, we now have here the elastic settlement or the immediate settlement, okay, which is now equal to the net applied pressure on the foundation, okay, which can be calculated by the foundation designer, okay, or the foundation engineer or the structural engineer, okay. They can provide that. Okay, then you have there the alpha, okay, we have defined that also. Okay, here you have your alphas, then you have your B prime here, and then you have your Poisson's ratio, and then the average take note. That's the average modulus of elasticity. Wherein we will have an example later, depending on the type of soil beneath the foundation. If it is a homogeneous soil, then we only have one elastic modulus. But if you have heterogeneous soil, then you can probably take the average, no? The average elastic modulus. Okay. And then here you have your I sub S or the shape factor. And then here you also have your I sub F, which is the depth factor. Okay. Yeah. Um, okay. Now, if you notice here that, okay, um, f sub 1, okay, f sub 1 and f sub 2 is basically a function of m prime and n prime, okay? So if we look at those equations, okay, then these equations can be referred also. If you don't want to calculate anymore, then you can just actually refer to these tables here, which is also found in your book, okay? Um, so depending on the values of m prime and n prime, okay, then you can calculate for f sub 1 and f sub 2. Now, take note in your book, if you have your book with you, the n prime here actually is the data still exceeds 3, but I just cut it off, no? Just to give you an overview of the table that you can find in your book. No? Okay. So again, if you don't want to calculate anymore these terms here, then you can just simply look at these tables. Okay. Okay. In your book. Okay. Now, also the variation of the depth factor. Okay. Is given in this table also. Okay, this one here, table 11.3 in your book. Okay. Um, so the depth factor is a function of the L over B. Okay. That's the length of the foundation over the width of the foundation, and as well as the embedment depth, that's D sub F, embedment depth of the foundation over the width of the foundation. Okay. And then you have here different values for the Poisson's ratio. If you, depending if you have zero point 0.3, point 0.4 or zero point 0.5. Okay, depending on the type of soil. Okay. Okay, so here there's a note that when the embedment depth is zero, that means yeah, the foundation is uh, on the ground surface. Okay, so let's go back here. So that means if d sub f is zero, so that means that the bottom of the foundation is on the surface, which is it's not normally done. Okay, normally we have embedment depth. Okay, to have some stability, but nevertheless, he mentioned here that if d sub f is zero, then the value of I sub f is equal to one in all cases. Okay, but in practice we don't have that. No? Okay. Um, Normally, the embedment depths that we encounter in practice is yeah, say for I guess for building structures. Normally, we have say from 1 meter to say 3 meters. Okay, but in overhead transmission line structures, for example, um, from these transmission lines. No? If you can see transmission lines or transmission towers rather, okay, distributing these transmission lines for the National Grid Corporation of the Philippines or the NGCP. These transmission towers normally the embedment depths there that we encounter are about 3 to 5 meters. Yeah. Okay, 3 to 5 meters. Um, say 1 to 3 meters can still be excavated by the normal backhoe equipments. But say 3 to 6 meters or 3 to 5 meters, normally we already use the long arm backhoe equipments to excavate for the foundation. Okay. Okay. Now, um, so then we have calculated now the elastic settlement for a flexible foundation, okay, which is given by this formula here. Okay, but if you have a rigid foundation, okay, then the elastic settlement of a rigid foundation can be estimated by this formula here, which is about 93% of the flexible settlement. Take note, this is at the center. At the center. Okay, so that's about 93%. Okay, or 0.93 of the flexible settlement. Okay. Now due to the non-homogeneous nature, okay, of soil deposits, the magnitude of the elastic modulus may vary with the depth. Okay. Now, for that reason, Bowles in 1987, okay, now the literature by Bowles is quite popular here in the Philippines. Okay. Now, Bowles recommended using a weighted average value for the elastic modulus. No? Okay. Wherein the average elastic modulus is equal to the sum of the elastic modulus for a particular layer multiplied by the depth of that layer. Okay. Okay. So you take all the sum over Z bar. Okay. Where E sub Si is now the soil modulus of elasticity within a depth Z. Okay. Within a depth of delta Z for a particular soil layer. Okay. Yeah. Because sometimes you can have a clay layer, then a sand layer, then silt layer, and a gravel layer. Okay. So they have different modulus of elasticity, for example. Okay. So when we prepare geotechnical reports, normally we we prepare we call it an idealized ground profile. Okay, wherein we try to group different soil materials for us to be able to provide their corresponding Poisson's ratio and elastic modulus for the settlement calculation. Okay. Okay. So Z bar is then equal to H or phi B, whichever is smaller. Okay. Yeah. So I think we have defined this one here. So again, this is your H. Okay. And then phi B is now 5 times the width of the foundation. Okay. Okay, so that's E sub S. So yeah, so E sub S we can substitute that value here. Okay, so it's the average. No? It can be the average. But if it is homogeneous, that means you only have one type of soil layer below the foundation. Then you don't need to take the average. No? It's just one value. Okay. So we now have here some representative values for the elastic modulus here. Say, for example, when you have a soft clay or a hard clay, or when you have a loose sand or a dense sand. Okay. So the soft and hard here refers to the consistency of cohesive soils. Okay. The loose and the dense sand here, or the dense description refers to the relative density of cohesionless materials. No? Okay. Yeah. So here you have the representative values, okay, of the Poisson's ratio as well, okay, or the mu sub s. Okay. So you have here a loose for a loose sand. This one is a medium dense sand. Okay. Because when we talk of relative density, you can have either very loose or medium dense, dense, and very dense. Okay. And then for consistency, you can have soft, very soft. You can have firm or medium stiff. Then you can have stiff and hard clays. Okay. Yeah. Normally we determine them during the geotechnical investigation. Okay. So here, when you say medium sand, that's a medium dense sand. When you say a medium clay, that's actually a medium stiff clay or a firm clay. Okay. 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 So so far we have discussed the basic formula for the elastic settlement or the immediate settlement. Okay. So and now let's talk a little bit about um, consolidation settlement. Okay. Now, when a saturated soil layer, okay, take note, we are referring to soils below the groundwater level, not saturated. Okay. Now, when a saturated soil layer is subjected to a stress increase because of the loads from your foundations or from structures or from equipment loads, okay, such as live loads, okay, okay, and some dead loads, then the pore water pressure is increased suddenly. Now, in the case of sandy soils that are highly permeable, the drainage caused by the increase in the pore water pressure is completed immediately. Okay. So pore water drainage is accompanied by a reduction in the volume of the soil mass, which results in settlement. Okay. Now, because of the rapid drainage of the pore water in the case of sandy soils, elastic settlement and consolidation settlement occur simultaneously. No? So magdungan sila kahitabo. No? Okay? Because of the rapid drainage. Okay? Now, in the case of a saturated, no? Okay? In the case of a saturated compressible clay layer, wherein it is subjected to a stress increase because of the effect of the foundations. Okay, say from the foundations of your house or of your building. Okay, so whatever foundation it is, whatever structure it is carrying. Okay, so when it is subjected to a stress increase, then the elastic settlement would occur immediately. Okay, that's with respect to the elastic settlement. But because the hydraulic conductivity of clay is significantly smaller than that of sand, okay, then the excess pore water pressure generated by loading gradually dissipates over a long or a longer period, no? Unlike in the case of sandy soils. Okay? Thus, the associated volume change, um, or rather the consolidation, okay, in the clay may continue long after the elastic settlement. Okay, yeah. So this settlement caused by consolidation in clay, again, may be several times greater than the elastic settlement. Okay. So this gradual process of drainage under an additional load application and the associated transfer of excess pore water pressure to effective stress would cause the time dependent settlement in the clay soil layer, which is now what we call as consolidation. Okay. And then the effect of that is consolidation settlement. The same as what you see here in this figure. Okay, I just took this from your book. Okay, don't worry about this. Okay, if you have your book, it's just the same figure. Okay, um, so because of the this additional load created by the foundations of the structure of your structure, then the pore water pressure here in the clay layer would then increase, and then eventually there will be drainage. Okay, wherein pore water will be slowly be expelled from the soil matrix. Okay, and then probably be drained above and below such layer. For example, if it is surrounded by sand layers above and bottom, okay, since the permeability of clay is smaller than the permeabilities of the sand, so it will try to drain, okay, itself slowly. Okay, so again, just to highlight this time effect of the the consolidation. Okay. Um, so here you have three cases wherein you have the case wherein you have a time t equal to 0. Okay. Wherein you have still here the total stress increase. Okay. Then plus the pore water pressure increase. Okay. But at time t equals to 0, still the stresses is not yet transferred into the effective stress. Okay. Yeah. So that means everything is still being carried out by the total stress. Yeah? Okay. As well as the pore water pressure. Okay. And then as time increases, okay, from between 0 to infinity, then the pore water pressure, okay, um, the pore water pressure increase will become smaller, and then you have the effective stress increase will start to be greater than 0. Okay, yeah, so that means water is so slowly being spelled out. Okay, from the soil matrix, and then the load is slowly being transferred to the the clay particles, no? Okay, the clay particles, okay, in such a way that the effective stress, okay, will start to increase. Then, as time is already very large, say up to infinity, give it enough time, okay, then the pore water pressure increase will already stop, okay, and then everything will now be transferred to the effective stress, okay, okay. So that means that everything will, all of the load is now transferred to um, the the soil particles, no? Okay, the clay particles for this matter. Okay, so that's why when we uh, do ground improvement, for example, in the case of clay layers, okay, um, normally we allow the clay to consolidate, no? By about say around 90% degree of consolidation, okay, before we put the structure. Otherwise, the structure will encounter very large consolidation settlements. Okay, I think in my experience, we have calculated consolidation settlement as deep as say, yeah, around 300 millimeters. Okay, that's about 30 inches, or about one ruler. Yeah? Okay, so you can just imagine if you have a house, and then your house will settle by about 300 millimeters. Then your door is opening outward. Then yes, you cannot open your door. Okay? You cannot enter your house. Okay. Okay. So here, this is just an example of a consolidation equipment. Okay. An odometer. We call it an odometer. Okay. An odometer measures the consolidation settlement of clay in the lab. Okay. So that means if you have a clay sample, okay, you can put it here. Okay. You can put it here. Okay, and then at the bottom we put some weights, okay, to generate some load, okay, and then try to measure the consolidation parameters, no? Okay, the consolidation parameters, which we'll be discussing in a while. Okay? In practice also, we when we encounter clay layers, we always specify to have them tested in the lab um, with consolidation test, no? For us to determine the consolidation parameters that we need for the consolidation settlement in the determination of the bearing capacities, no, or the shallow bearing capacities. Okay. Okay. So here in this figure, so here we see the time deformation plot during consolidation for a given load increment. So basically, with respect to the time deformation plot, we can divide the time log uh, into three stages. Okay, so if you can see this curve here, okay, so we have here the first part of the curve is now what we have as a stage one, or the initial compression, okay, of the clay layer. And then from here, on this part of the curve, okay, this is now your primary consolidation. This is now your stage two, okay. And then on this part of the curve, okay, wherein it starts to be constant, okay, then this is now your stage three or the secondary consolidation. Okay. Yeah. So for this figure here, okay, let's try to go back to this one. I think that's being explained here. Okay. Yeah. So that figure, okay, figure 11.10 in your book as well. Okay. If you want to check with your book, okay, that is figure 11.10. It shows the shows that the upper part of the we call this the basically we call this the E log P plot. No? Okay, this is your effective pressure. Okay, we call this the E log P plot. Is somewhat curved with a flat slope, followed by a linear relationship for the void ratio with the logarithm of the effective pressure having a steeper slope. Okay, so if we go back to this figure here, okay, if we try to plot the void ratio with respect to the effective pressure, the sigma prime, no? Okay, that's this we call this the E log scale. No? This is in log scale. This is in linear scale. This is in log scale. Okay, we call this the E log P. Okay, E log P plot pressure. Okay, plot. Okay. So here initially we have a yes. So initially um, okay, we have this part of the curve. Okay, okay, this part of the curve, and then we have the next this next part of the curve. No, where the curve starts to be linear. Okay, so the reason for this is actually explained here. Okay, now a soil in the field at some depth has been subjected to a certain maximum effective past pressure in its geologic history. Okay? Now, this maximum effective past pressure may be equal to or less than the existing effective overburden pressure at the time of sampling. When we get the samples, okay, during the geotechnical investigation. Okay. Now, the reduction of the effective pressure in the field may be caused by natural geologic processes or human processes. Okay? Now, during the soil sampling, when we do geotechnical investigations, during the soil sampling, the existing effective overburden pressure is also released, which results in some expansion of the soil. No? The soil can expand. Okay. Okay? Especially when you have expansive clay soils. Um, Now, when this specimen is subjected to a consolidation test, okay, and then a small amount of compression, or that is a small change in the void ratio, will occur when the effective pressure applied is less than the maximum effective overburden pressure in the field to which the soil has been subjected in the past. So thus we have this behavior here. Now, that's the reason for this behavior. Okay, you only have a minimal change in the void ratio. Okay. Now, when the effective pressure, okay, or the pressure that you apply during the consolidation test, now when the effective pressure applied on the specimen or the soil specimen here, okay, applied on the soil specimen, becomes greater than the maximum effective past pressure which the soil experienced in the past, okay, or way before, okay, then the change in the void ratio is much larger, and then the E log P plot or the E log P relationship would then be practically be linear with a steeper slope. So that's now this part of the curve. Okay. So that means you have here two. two parts of the curve. No? If this is now the break, okay, this is now the break, then this one is one part of the curve, and then this one is another part of the curve. And then this boundary here would then tell us the what we call the pre-consolidation pressure, which we'll try to derive later. Okay, we call it the pre-consolidation pressure for us to determine the OCR value, no? The over consolidation ratio. Okay, because the over consolidation ratio will tell you if you are having a normally consolidated clay material, for example, or an over consolidated clay material. And then the consolidation settlement formulas for these two are quite different, no? Between a normally consolidated clay and an over consolidated clay material. Okay, so again, such a relationship can be verified in the laboratory by loading the specimen to exceed the maximum effective overburden pressure. Okay, and then we do some unloading and reloading process. Okay, so for example, here in the figure 11.12 in your book, we have here an example of an E log P plot, okay, an E or the void ratio versus the effective pressure plot in the log scale, the sigma prime, okay. So here we now try to exceed the maximum past effective pressure, okay, in such a way that you will have this curve here. And then we subject it to an unloading process. So we release the load in the consolidation test. Okay, so we release such load, and then the soil will try to rebound, and then you will have this curve here, an unloading process. And then again, we load the sample. Okay, we reload the sample, and then the sample will follow again this settle this yeah this change in the void ratio here. Okay, yeah. So we have here an unloading curve and then reloading curve. So you have here the loading curve, unloading curve, and then a reloading curve. Okay. Now, because of these processes, we now have here these two basic definitions of clay based on stress history. Okay. So based on stress history, you can again either have a normally consolidated clay or an over consolidated clay. Okay. Now, for a normally consolidated clay, in this case, the present effective overburden pressure. Okay, so that's basically the pressure created by the existing soil on top, no? On top of the soil material that you're considering with. Okay? So that present effective overburden pressure is considered as the maximum pressure that the soil was subjected to in the past. Okay. Now, when we say over consolidated, then in this case, the present effective overburden pressure is less than that which the soil experienced in the past. Okay. So in this case, the maximum effective past pressure is called the pre-consolidation pressure. Okay. So, which means now when you say over consolidated, then the existing soil on top of the soil material that you're considering with, okay, is lesser than the um, the is lesser than the effective past pressure that the soil experienced before. Okay, so that's why it is over consolidated. Okay, now again, to determine between normally consolidated and over consolidated, then we need to know the OCR value, no? Or the over consolidation ratio. Okay, wherein you will have the formula for that in a while. Okay, now, so for the over consolidation ratio or the OCR for a soil can now be defined as the ratio of the pre-consolidation pressure of a specimen, okay, over the present effective vertical pressure, okay, wherein the present effective vertical pressure can just be calculated by the unit weight of the soil multiplied by the height of the soil. Okay. But for the pre-consolidation pressure of the specimen, if you have the E log P plot, okay, for example, this one here, your E log P plot, you can also determine the pre-consolidation pressure. So the procedure for that is this one here. Okay, so first, by visual observation, we can establish a point A at which the ELOP plot has a minimum radius of curvature. Okay, this you learned in differential calculus. Okay, so the minimum radius of curvature. So this one here, in this case, in this curve, this is the minimum radius of curvature. Okay, so you plot a you plot there a horizontal line AB. Okay, so in this minimum radius of curvature, we plot a horizontal line AB, that's this line. Okay. The next, we draw the line AC tangent at A. Okay. So we draw this line AC tangent, no? So a tangent line to A. So then you now have two lines. This one here, AB and AC. Okay. Then we draw the line AD, which is the bisector of the angle BAC. Okay, so if you now have this angle here, BAC, so we draw a bisector, an angle bisector. We draw a line here, which we call AD now. This is now the angle bisector. Okay, and then we project the straight line portion GH of the A log B plot back to intersect line AD at point F. So that means here, if you now have here a relatively straight line, okay, in this part of the curve, you try to project a straight line here back. Okay, try to project. I hope you're seeing my cursor. You try to project a straight line here back in such a way that it will intersect the angular bisector. Okay, yeah, this one here. So in such a way that they will meet at point F. Okay, and then from there, this point, you now try to project it down to determine the sigma sub C prime or the pre-consolidation pressure. Okay, so then we can substitute that one here, okay, in this formula. So here we see now the two characteristics, no? The two consolidation characteristics. In this case, for a normally consolidated clay, and then this one for an over consolidated clay. Okay. Here for the normally consolidated clay, we now call this the virgin consolidation curve. Okay, the virgin consolidation curve, wherein the slope for this virgin consolidation curve is now what we call the um, C sub C or the compression index. Okay, and then this one here also is the consolidation curve in the case of a remolded specimen. Huh? Okay. Yeah. So this is now yeah the this is the laboratory consolidation curve. Okay. Now in this curve, the um, the pre-consolidation pressure at this point is equal to the effective overburden pressure. The present effective overburden pressure. Okay. Now, in the case of the over-consolidated clay, okay, so if you now have this as your laboratory consolidation curve, okay, then this one here is again your virgin consolidation curve, okay, with a slope equal to C sub C or the compression index, okay. But in the case of an over-consolidated clay, you can have a laboratory rebound curve, this one here, where the soil can rebound or can expand, okay? And then this part of, or the slope of this curve is now what we call C sub S, or the swell index, okay? Swell index. So with respect to this curve, if you project this up and then intersect it here, okay, with respect to the virgin consolidation curve, okay, so this intersection here is now what you call as the pre-consolidation pressure, okay, in the pressure plot, okay, and then if you project it here, okay, with respect to this is now your initial rather. Okay, the E sub O is your initial void ratio. Okay, if you project this line here, intersect it on the line with the initial void ratio, then yes, that can now be your present effective overburden pressure. Okay, wherein in this case, with respect to the initial void ratio, then the present effective overburden pressure is equal to the pre-consolidation pressure. Okay. And then at this point here, okay, this point here at point F and at point K is equivalent to zero point 0.4 or 40% of the initial void ratio. Okay. So let's try to go back to these figures later when we try to derive now the formulas for the consolidation settlement. Okay, so to derive the formulas for the consolidation settlement, so let us now try to consider a saturated clay layer of thickness H and a cross-sectional area under an existing average effective overburden pressure sigma prime sub O, okay, which is just equal to the unit weight times the height, okay. So that's actually this one here, okay. We have now this figure, okay. So you now have here the soil element with a height H, okay, and a cross-sectional area A. I hope you're seeing my cursor. Okay. So this one here is yeah, are the soil. Okay. Now this part here is now the void, and then this colored dotted area here is now the solid phase. This is the solid particles. This is now the voids. Okay. Now, because of an increase of effective pressure, delta sigma prime, caused by your foundations, then we can now have our primary settlement, which is equal to S sub C, wherein from this initial position, okay, from this initial position, then we will now have a primary settlement, S sub C, wherein we now have, wherein the soil element will now reduce in height. Okay, wherein this is now the new uh, elevation or the new height of your soil element. Okay, now between these two heights, okay, caused by the primary settlement, then you can also have your change in the volume. No? Okay, the change in the volume. Okay, from the initial volume, okay, to the say the final volume V sub 1. Okay, this one here. Okay. So that means the change in the volume is equal to V sub 0, where this is now the initial volume, minus V sub 1, which is now the final volume. Okay. So the initial volume is equal to the height times the area. Then the final volume is equal to the height minus the primary settlement, which is this one. Okay. Uh, the height minus the primary settlement will give you this height here multiplied by the cross-sectional area. That's your final volume. No? Okay. That's your V sub 1. Okay, this one here. Okay, V sub 1. Okay. And then if we subtract these two, then we will just get the change in volume is just equal to the primary consolidation settlement multiplied by the area. Okay. Now, the change in the total volume is just equal to the change in the volume of the voids as well, no? Or the delta V sub V. Okay? So that means this equation here, equation 11.23, is just equal also to the change in the volume of voids. Okay, or that's the change in the volume of voids, which is demonstrated here. Okay, yeah, the volume of the okay, say sorry, yeah. So you have here the initial void volume. Okay, you have here the initial void volume, and you have here the final void volume. Okay. So that change in volume, which is the same as this one, which is equal to S sub C times the area, is also just equal to the change in the void volume. No? If we now try to separate this one, the soil with respect to voids and the solid part. Okay. Now we know that by definition of the void ratio, the void ratio is equal to the volume of voids over the volume of solids. Okay. Or the volume of voids is equal to the void ratio times the volume of solids. Which means that if there is now a change in the volume of voids, then there is also a change in the void ratio. Okay. Now, the volume of solids can have the equation equal to the initial volume over 1 plus the initial void ratio. So the initial volume is equal to the area, sorry, it's equal to the area times the height. Okay, that's this one here. That's the initial volume. Okay, that's the initial volume. Okay. And then E sub O is the initial void ratio at the initial volume. Okay. So if we now substitute equation 11.23 in your book to equation 11.26 here, okay, okay, so then we now have the the change in the volume, okay, the change in the volume is now equal to the primary consolidation settlement times the area, which is now equal to the change in the void ratio multiplied by the volume of the solids. Okay. But the volume of the solids is now equal to this one here. Okay. So that means we now have this one multiplied by the change in the void ratio. Okay. So which means now that if we now equate this term here, because we want to derive the formula for the primary consolidation settlement, if you want to equate this term here with this term, then the area can be cancelled out. So the primary consolidation settlement is now equal to this equation here now, okay, which is now the height of the soil element, okay, multiplied by the change in the void ratio over 1 plus the initial void ratio. That's E sub O. Okay. So again, this is now your H. Okay. Your H. And then this change in the void ratio is now the change in the volume of the voids. Okay. Now, okay. So with that, let us now try to focus on this formula here. Okay. So with that formula, for normally consolidated clays that exhibit a linear E log P relationship, okay, okay, where is that? If we go back here, okay. So this one here, no, this one, okay, yeah. So there we can see that the change in the void ratio, okay, would be equal to the compression index, which is basically the slope of this E log P plot. Yeah, this is now your C sub C. Okay. Um, okay. Multiplied by the log um, of the present effective overburden pressure, okay, plus the increase in stress due to the foundations, okay, due to the foundation pressure, that's the increase in stress, minus the log of the effective overburden pressure, which is just equal to, say, the unit weight times the height, okay. So if we now substitute this equation here, we replace it here in this delta, the change in the void ratio, then we now have uh, your C sub C, okay, C sub C here, that's your C sub C. Then you have your H over 1 plus E sub O, that's this one, H plus 1 over 1 plus E sub O. And then this term here can also be rewritten by this term here, okay? Considering your logarithmic logarithmic properties. No? Okay, so these two are just the same. Okay, so here in this formula, this is now the compression index. Okay, compression index, then the height of the soil specimen. Okay, and then this is now the initial void ratio. This is the present effective overburden pressure, which can just be the unit weight times the height. Okay, and then this is now the stress increase generated by your foundation. Okay. Now, in over-consolidated clays, okay, so in the case of over-consolidated clays, so this one here, in the case of over-consolidated clays, which follows this behavior, okay, then we now have two cases. The first case is when the present effective overburden pressure plus the stress increase is less than the pre-consolidation pressure. Okay. Then in this case, the field E log P variation will be along the line HJ, which is now the slope, which is approximately equal to that of the laboratory rebound curve. Okay. And then the slope of that rebound curve is now C sub S, which we now call as the swell index. So that means if you have this condition here, then that means you are basically following this curve. No? Okay? In such a way that the present effective overburden pressure plus the effective stress, okay, plus the effective stress, the increase in stress, okay, is less than, less than the pre-consolidation pressure. Okay, this one here. Okay, so it would fall. It would fall under this curve. Okay, so that means um, we follow this formula here for the change in the void ratio, but instead of using the compression index, we use the swell index. Okay, so that means you now have the equation for the primary consolidation settlement in that scenario. Okay, wherein this is now the swell index. Now, if the the present effective overburden pressure plus the increase in stress is greater than the pre-consolidation pressure, so that means okay, so that means the present effective overburden stress plus the increase in stress. Okay. If you sum the two, then it will be greater than the pre-consolidation pressure. So it's somewhere here. It's already somewhere here. Then it would fall in this curve. Okay. Yeah. So in that case, then the formula for the primary consolidation settlement, okay, is now equal to the swell index multiplied by the height of the specimen over 1 plus the initial void ratio multiplied by the log of the ratio of the pre-consolidation pressure over the present effective overburden pressure, okay, plus the compression index multiplied by the height of the specimen over 1 plus the initial void ratio E sub O multiplied by the log of the sum of the present effective overburden pressure plus the change in or the stress increase. Okay, the stress increase, or in practice we call it the structural bearing pressure. Okay, generated by your foundations over the pre-consolidation pressure. Okay. So these are now then the two formulas in the case of a normally consolidated clay, an over-consolidated clay, and this is the formula for a normally consolidated clay. And between normally and over-consolidated clay, we can determine them using the OCR ratio, no? Or the over-consolidation ratio. Okay. Okay. Now, if we look at the figure here, let's go back. If we look at the figure here, after the primary consolidation settlement, then the next stage is the secondary, okay, the secondary consolidation settlement. Okay, so far we have derived the formula for this primary consolidation settlement, depending if you have normally consolidated or over consolidated clay soils. Okay. Then after that, depending on the type of soil, again, you can either have a secondary consolidation settlement or not. Okay. Now let's talk a little bit about the secondary consolidation settlement. Okay. Now, so at the end of the primary consolidation, so that is after complete dissipation of the excess pore water pressure, some settlement is or some settlement can still be observed, and that is because of the plastic adjustment of the soil fabrics. Okay. Now, this stage of consolidation is called the secondary consolidation. Okay? Now, during secondary consolidation, the plot of the deformation against the log of time would be practically linear. Okay, that's what we have seen earlier. Okay, and then the variation of the void ratio E with time for a given load increment will be similar to that shown in figure 11.8. No? If you can just look at it in your book as well. Okay. Okay. Now, this variation is shown in this figure here. Okay. Yeah. So, so again, this is now the stage one. Okay, the stage one of your settlement. Then this is now your stage two. This is the primary consolidation settlement, and then this part here is now your secondary consolidation settlement. Okay, wherein here in this curve we can try to get our C alpha. Okay, C alpha, where C alpha is the ratio of the change in the void ratio over the log of uh, the time element, no? Between t sub 2 and t sub 1. Okay, between the final time and the initial time. Okay, so so with that, we have the C alpha, where C alpha is now the secondary compression index, and then delta is the change in the void ratio. Okay. So then with C alpha, we can calculate the magnitude of the secondary consolidation settlement with this formula here symbolized by SLS, secondary consolidation settlement, which is now equal to H, okay, H, which is the height of the soil element, multiplied by the log of the final time over the initial time, multiplied by C prime alpha, where C prime alpha is equal to C alpha over 1 plus E sub P, where E sub P is this one here. Okay, this is the void ratio at the end of the primary consolidation. No? This one here. Okay, so this is now basically the end. No? This is the end of your primary consolidation, wherein after this one, this is the start of the secondary consolidation. Okay, so this is now your E sub P, and then C alpha here is basically this one. No? This is the formula. Okay, or basically, or this one here. And this is your C alpha. Okay, so that's this formula now. Okay. Now, secondary consolidation settlement is basically more important than primary consolidation settlement in the case of organic soils. Okay, if you recall, in our USCS classification, we have their organic soils and also highly compressible inorganic soils. Okay. Now, in the case of over-consolidated inorganic clays, then the secondary compression index is very small and of less practical significance. Okay. 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 So, so far, we have discussed no, the three types of settlements. Okay. The immediate or the elastic settlement, and then the two consolidation settlements, which are the primary consolidation settlement and the secondary consolidation settlement. Okay. Now, with those equations, we don't have any information regarding the rate, no, of primary consolidation. Okay, so how long does the soil consolidate? No, we call it the rate of the primary consolidation. So to determine that, Terzaghi in 1925 proposed the first theory to consider the rate of one-dimensional consolidation for saturated clay soils. Okay. Yeah. Now, the mathematical derivations for these equations are based on the following six assumptions here. Okay. So these assumptions are first, the clay water system is homogeneous. Okay. And then saturation is complete. Okay. So that means you have a fully saturated soil, which is below the groundwater level. Okay. And then compressibility of water is negligible. That means water will not compress. Okay. Compressibility of the soil grains is also negligible, but the soil grains can rearrange. Okay. And then the flow of water is in one direction only. That is in the direction of compression, normally in the vertical direction, no? In the same direction of the application of the load in the case of foundations. And then also Darcy's law is valid, as what we have discussed um, when we discuss permeability. Okay. So so this figure here shows a layer of clay of thickness 2 HDR, wherein HDR is now considered the length of maximum drainage path that is located between two highly permeable um, sandy layers. Okay, so we now have this one here. Okay, yeah. So this is now your clay layer. Okay, your clay layer with a height of 2 HDR, for example. Okay, okay. So let's now try to consider a point A. No, a point A here. Okay, so let's say this is now your point A. Okay, wherein if we put here an imaginary piezometer, okay, it will have a certain um, pressure head. Okay, pressure head. And then that point A is measured at the depth, or sorry, at a distance C from the bottom of the clay layer. Okay. So if the clay layer is subjected to an increased pressure of delta sigma, okay, so that's this one here, huh? Because of the effect of your foundation pressure. Okay, then you will have a stress increase. Okay, then the pore water pressure at any point A in the clay layer will increase. Okay? Now, for a one-dimensional consolidation, water will be squeezed out. Okay, because that's the effect of consolidation. Water will be squeezed out in the vertical direction toward the sand layer. Okay, so yeah, so water will be um, expelled here in the sand layer. Take note, this is your groundwater table. Okay, so water will be squeezed out from the clay layer. Okay, so this figure here shows a prismatic element. If you now try to enlarge a certain soil element here at point A, so this is now an enlarged soil element. Okay, yeah. So so this element has the dimensions dx, dy, and dz. Okay, and then water is squeezing out. For example, in this direction here, water is going up into the sand layer because water is squeezed out from the clay layer because of the effect of this stress increase, no? Because of the foundation loads. Okay. Um, okay. So in that soil element, okay, we can have now the rate of outflow of water, okay, minus the rate of inflow of water would be equal then to the rate of volume change. No? Wherein this is now your rate of outflow of water, and then this is now your rate of inflow of water. And this change would then be equal to the rate of volume change. Yeah? Okay, the difference between these two flow rates, sorry, I'm sorry about that. The difference between these two flow rates, okay, will be equal to the rate of volume change in your clay layer. Okay, so take note, we are trying to derive the rate of primary consolidation, which is a function of time. Okay. Okay, so with this equation or with this equation here, then we now have the rate of outflow minus the rate of inflow is now equal to the change in volume with respect to time. Okay, so where V is the volume of the soil element, and then V sub Z is the velocity of flow in the vertical direction, Z direction. Okay. So if we just simplify this one, then we get this equation here. Okay. And then applying Darcy's law. Okay. So, okay, Darcy's law is valid. Applying Darcy's law, then we have the velocity is equal to K times I. Okay. Where I is the hydraulic gradient and K is the coefficient of permeability or the hydraulic conductivity. Okay. So we can replace the hydraulic gradient by negative um, okay, negative partial derivative of h with respect to z. Okay, this the okay, that's the pressure head with respect to z. Okay, but the pressure head is just equal to the pore water pressure over the unit weight of water. Okay, that's the definition of pressure head. Okay, where U is now the excess pore water pressure caused by the stress increase. No? Okay, caused by this stress increase. Okay? Okay, now if we now substitute equation 11.44 to equation 11.45, then we get this equation out here, okay, where we now have the second partial derivative of the excess pool water pressure with respect to the depth Z. Okay. Then we now have here the first partial derivative of the volume of the soil element with respect to time. Okay. And then this is now the volume of the soil element. This is the unit weight of water. Then this is now the permeability of the soil. Okay. Or the coefficient of permeability or the hydraulic conductivity, no? Which we discussed in permeability of soils. Okay. 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 Now, during consolidation, the rate of change in the volume of the soil element um, is equal to the rate of change in the volume of voids. Okay. In such a way that, yeah, the rate of change of the volume of the soil solids is equal to the rate of change of the volume of voids. Okay. Now the rate of change of the volume of voids. Okay. Now the volume of voids can be also written by this one here in terms of the volume of solids plus the void ratio multiplied by the volume of solids. Okay. With respect to time. And then if we just expand this, just applying the derivative of sum, no? Okay, if you recall in your differential equation, differential calculus, okay, you have the the derivative of sum and then derivative of a product, okay, or derivative, yeah, okay. Um, so those derivatives, okay. So in this case, if we now try to expand this one, then we now have this equation here, okay. Now, with such equation, we can assume that the soil solids are incompressible. Okay, if we go back to the assumptions, the compressibility of the soil grains is negligible. Okay, so that means this change here in the volume of solids is negligible, or that is equal to zero, or the change is zero with respect to time. Okay, now again, the volume of, so that means this one here is zero. Okay, this one here is zero. This one here is also zero. What is left is this one here. Okay, but V sub S is equal to the volume of solids is equal to the total volume over 1 plus the initial void ratio. And considering our soil element, then the soil element has dimensions. Where's that? Has dimensions dx, dy, and dz. Okay, so these are now the dimensions. Okay, and so if we substitute this one um, here in this formula, okay, then V sub s is equal to this one, which is this one here, and then you now have the first partial derivative of the void ratio with respect to time. Okay, where E sub O is the initial void ratio. Okay. So if we now substitute this equation here to this equation, then we will get equation 11.49. Okay. Okay. Now, so in this equation 11.49, now this change in the void ratio, okay, let's have that one here. Now, the change in the void ratio is caused by the increase of the effective stress, no? Which is in relation to a decrease of the effective pour of the excess pour water pressure. No? Okay, if you try to if you try to recall here, where was that? Yes, this one here. You have now an increase in the effective stress is equivalent to a decrease in the pore water pressure. Okay, so that's this one here. So that means the increase, so the change in the void ratio, okay, which is equal to the increase in the effective stress, okay, is equal to the decrease in the pore water pressure. Okay, multiplied by the coefficient of compressibility A sub V. Okay, yeah, A sub V. Okay, so that means we can substitute this one here in this equation. So we no longer have this void ratio, this term here. We no longer have this void ratio, and that is now being replaced by this term here. Okay, this term. Okay, so that means we now have A sub V. Sorry, we now have A sub V here over 1 plus E sub O. Okay, so this A sub V over 1 plus E sub O, okay, can be written by M sub V, where M sub V is now what you call the coefficient of volume compressibility, which is equal to the, which is now equal to this one. This is now the coefficient of compressibility over 1 plus the initial void ratio. Okay. Okay. Or We now have this one here, M sub V, okay, where M sub V, okay, um, if we now have K over M sub V divided by the unit weight of water can just be written as C sub V, okay, or that is now the coefficient of consolidation. Okay. Yeah. So that means these terms here can just be replaced by coefficient of consolidation C sub B. Okay. Then we now have this final equation here, no? Which is now a partial derivative. Okay. Partial derivative. Okay. With respect to the excess pore water pressure. Okay. So A sub V here, M sub V, and C sub V are what we call the consolidation parameters, no? Which we can derive when we try to do consolidation tests in the laboratory. Okay. In the lab, we can also determine the initial void ratio. Okay. So this equation 11.52 is now what we call the basic differential equation of Terzaghis consolidation theory, okay, which can be solved with the following boundary conditions if you try to recall your subject in differential equations. Okay. So in differential equations, we can normally solve the differential equation if we have boundary conditions. Okay. So here for our boundary conditions, if Z is equal to 0, then the pore water pressure is, or the excess pore water pressure is 0. Okay. And then if Z is equal to 2 HDR, then the initial excess pore water pressure is also 0. Okay. And then at time equal to 0, then the initial, then the excess pore water pressure would now be equal to the initial, no? Okay. The initial excess pore water pressure 0, where Z is derived, where this Z is derived from the bottom of the clay layer. So, okay, so this is now at Z equal to 0. This is now at Z equal to 2 HDR. Okay. So at Z equal to 0, the excess pore water pressure here is 0. At Z equal to 2 HDR, the excess pore water pressure here is also 0. Okay. And then at time T equal to 0, then the excess pore water pressure is equal to the initial excess pore water pressure. Okay. So with these boundary conditions, you substitute it here in solving this differential equation for the Terzaghi's consolidation theory, then that solution would yield this equation here, which is a nice looking equation. Okay. So here, M here is an integer from 0 to infinity. U sub O is the initial excess pore water pressure. Okay. And then M here is equal to this formula here. Okay. Z is your distance, no, from the bottom of the clay layer. Okay. And then TV here is your time factor, which is a non-dimensional number, which is equal to your TV. Now your time factor is equal to C sub V times T, which is your time, over HDR. No? Okay. HDR squared, no? Where HDR is derived from here. No? This is your depth of drainage. Okay. And then CV is your coefficient of consolidation equal to the hydraulic conductivity over the unit weight of water multiplied by the coefficient of volume compressibility, which is equal to the coefficient of compressibility over 1 plus the initial void ratio. Okay. Okay. Now, because consolidation progresses by the dissipation of excess poor water pressure, take note, okay? Consolidation only progresses if there is dissipation of excess poor water pressure. Okay? Okay, so in that case, then the degree of consolidation at a distance z, okay, at any time t is now equal to this equation here, okay, where this is now the degree of consolidation, okay, and then U sub O is again the initial excess poor water pressure. Um, then U sub Z is the excess poor water pressure at time T, okay. So if you now combine equation 11.55, this one here, the U, okay, substitute it here in equation 11.57, this one here. So we substitute this value of U here, you know, with respect to time. Then we can obtain the degree of consolidation at any depth Z. Okay, so that is at we can get the degree of consolidation at any depth Z. This is your depth Z. Okay, at any time T. Okay, and so yes, this is that is being um, shown in this figure here. So this is now the variation of the degree of consolidation. Okay, the degree of consolidation use of Z with respect to any depth Z, okay, with respect to any depth Z, and with respect to any time T, no? Indicated by the time factor, where this is now the time factor at equal to 0. This is now the time factor equal to zero point 0.1, zero point 0.2, zero point 0.3, and zero point 0.4, and so on and so forth. Okay, or take note, T sub V is your time factor. And then from T sub V, you can calculate your time. Okay. And then Z over HDR is your ratio. Which means that if Z over HDR is 1, then that means I'm referring to this point here. Okay. Where Z is equal to, sorry. I'm referring to this point here pala, no? Because this is 2 HDR. Okay. So this depth is 2 HDR. So 1/2 of that is HDR. So when Z over HDR is equal to 1, then I'm referring to this point. Okay. And that is this one here, a value of 1. Okay. So now to get the average, no? The average degree of consolidation for the entire depth of the clay layer at any time t, um, as given in equation 11.57, can now be given by this equation here. Okay, where U now is the average degree of consolidation. Okay, and then S sub C T is the settlement of the layer at time T, and then S sub C is the ultimate settlement of the layer from primary consolidation, which is now given by this equation here. Okay, yeah, where we now have 1 minus quantity 1 over 2 HDR, where 2 HDR is this one here, the depth of the clay layer. Okay. And then we integrate. No? We now integrate U sub Z, okay, dz all over the um, initial excess pour water pressure. Okay, where U sub Z here, we can substitute this formula. Okay, so um, solving this one, then um, we can now get the formula now for the average, no? Okay, for the average degree of consolidation with respect to the non-dimensional time factor. Okay, so again, m here is a constant. We have this m again. What is that m? That's this one here, with respect to m. Then you now have your time factor, no? Okay, which is given in figure 11.26. Okay, that's this one here. Okay, so this is now the graph of the average degree of consolidation with respect to the time factor given by this equation here. Okay. Okay. So that figure, this one here, 11.26, okay, in your book, represents the case where the initial excess, per water pressure is the same for the entire depth of the consolidating layer. Okay. Now, if you look at figure 11.26 in your book, okay, this one here, we can see that um, for the average degree of consolidation, okay, for the average degree of consolidation from 0 to 60%, okay, from 0 to 60%, that's this curve here, okay, 0 to 60%, then the time factor, this time factor can be given by this equation here, okay? And then for the average degree of consolidation greater than 60%, okay, that's greater than 60% from this point downwards here, okay, from this on this part of the curve, then the time factor uh, can be given by this equation, okay, with respect to the average degree of consolidation. Okay, and then after you have solved the time factor, then we can solve for the time. Okay, yeah, um, which is now uh, the rate, no? The time rate of primary consolidation. Okay. Okay, so don't worry about these graphs because yeah, all of these are found in your book. Okay, I've just taken this in. Okay, so yeah, just a time check. So I think we can still have some problems. Okay, let's okay. Okay, so here we have an example. Okay, so here we have an example of a rigid shallow foundation, a 1 meter by 1 meter in plan. Okay, Um, um, then we have an embedment depth of 1 meter. Okay, so the foundation is a square foundation, 1 meter by 1 meter with an embedment of 1 meter as well. Okay, and then the foundation bearing pressure or the stress increase is equal to 200 kilopascals. Okay, and then we have here the Poisson's ratio of the soil is given as 0.3. Okay. Um, but the elastic modulus is quite different from 1 to 2 meters, which is about 8,000 kilopascals. And then from 2 to 3 meters, the elastic modulus is about 6,000 kilopascals, that's kilonewtons per square meter. And then from 3 to 5 meters, the elastic modulus is 10,000 kilopascals. Okay. And then this depth from the bottom of the foundation down to the competent material, which is the rock layer, is about 5 meters. Okay. Yeah. Which is also the same as 5B. No? 5 times the width of the foundation. In this case, your width of the foundation is 1 meter. Okay. Which is just equal to H. Okay. So since we have different elastic modulus, okay, then we can try to get the average um, elastic modulus, okay, using this formula, okay, wherein this one here is just the sum of the individual, no? Okay, individual layers. No? Okay, so this is now, for example, 8,000 times 2 meters, okay, plus 6,000 times 1 meter, because you have here 2 meters, 1 meter, and 2 meters. Okay. Okay. Then so that's 8,000 times 2 plus 6,000 plus 1 plus 10,000 times 2 all over z bar, where z bar is 5 meters, no? Equal to 5 times the width of the foundation, which is 1 meter. So then from there, we can get the average elastic modulus. Okay. So we are asked to calculate the settlement at the center of the foundation. So at the center of the foundation, if you recall, alpha is equal to 4, m prime is L over B, which is just 1 over 1, which is 1. And then n prime is equal to h, where h is equal to 5 meters. Okay, that's h is the distance between the depth of the foundation, at the depth of the bottom of the foundation down to the competent material, no? Which in this case, the rock layer, okay, the rock layer, wherein you now have, you don't have much settlement that will occur, okay? Okay, and then you have here b over 2, so in such a way that n prime is equal to 10, okay? And then from tables 11.1 and 11.2, we can determine the values of f sub 1 and f sub 2, as I have shown earlier. Okay. And then from there, we can, oh yeah, we also know the Poisson's ratio that is given. Okay. And so then we can compute for the shape factor, which is 0.507. Okay. And then from table 11.3, we can get also the depth factor. Okay. Wherein the ratio of the embedment depth, d sub f, over the width of the foundation is 1 over 1, equal to 1. And then L over B, that's the length over the width, is equal to 1. And then Poisson's ratio is equal to 0.3. So take note, that's 1 and 1 and 0.3. So the value is 0.65. Is that correct? Let's see. Where's that? So that is L over B is 1. df over b is 1. So that's 1 and 1. Poisson's ratio is 0.3. So then the value of the depth factor is 0.65. Okay, that's correct. Okay, so that's 0.65. Okay. So then if we now substitute the formula for the elastic settlement considering flexible foundations, Okay, then we now have here the stress increase, which is 200 kilopascals. Okay, that's taken from here. That's the stress increase, okay, due to the load of your structure transmitted into the foundation pressure. Okay, that's usually calculated by the structural engineer. Yeah. Then you have alpha, which is 4 at the center of the foundation. B prime is the width of the foundation over 2. That's 1 meter. That's the width of the foundation. Then Poisson's ratio is zero point 0.3. The average elastic modulus is this value here, as calculated. And then these are now your shape factors and depth factors, no? Taken from here, from the tables. So that gives me an elastic settlement of 14.3 or 0.0143 meters, or that's 14.3 millimeters. Okay. And so, since the foundation is rigid, okay, so we have a rigid foundation. So since the foundation is rigid, then the elastic settlement for the rigid foundation is about 93% of the elastic settlement of the flexible foundation, which is yeah, about 13.3 millimeters. Okay. So normally, our settlement criteria for shallow foundations is around 25 millimeters. So that means this result is okay. Yeah? If we only have elastic settlement, okay, then we are fine. Okay? Otherwise, if it will exceed the settlement criteria, then that's the time wherein we start to recommend ground improvement techniques. No? Okay, and then there are a lot of ground improvement techniques, um, but this we teach in the masteral degree program. Okay, then you can recommend that. Also, when we prepare geotechnical reports, if we find these conditions, then we try to suggest ground improvement techniques depending on the type of soil that we have encountered during the geotechnical investigation. But again, this is just elastic settlement. Nah? The settlement criteria is based on total settlement, which is also the sum of the consolidation settlement. Okay. Now, to have an example of consolidation settlement, we have here an example. Um, so we have here a soil profile, okay, um, with a uniformly distributed load delta sigma of 100 kilopascals applied at the ground surface. Okay, then we are asked for the settlement of the clay layer caused by primary consolidation. If in A, in we have three cases. For letter A, the clay is normally consolidated. B, the pre-consolidation pressure, sigma prime sub C, is 200 kilopascals. And C, the pre-consolidation pressure is 150 kilopascals. Now, for our ground profile, we have here a swell, a sandy material, okay, on top. Okay, that's this one here. We have a sandy material on top of the clay material at the bottom. Okay, then for the sandy material, you have here the groundwater level or the groundwater table. So that means above the groundwater table, about 2 meters depth, you have the dry unit weight of the soil, which is about 14 kilopascals. And below the groundwater level, you have a saturated unit weight of 18 kilopascals with a depth of 4 meters. Okay? And then the depth of the clay layer is about 3.5 meters with a saturated unit weight of 19 kilonewtons. Sorry, this is kilonewtons per cubic meters rather. Okay, not kilopascals. Okay, that's 19 kilonewtons per cubic meter since this sand and clay layers are below the groundwater table. Okay, and then the clay layer has a void ratio of 0.8. This is probably your initial void ratio, your E sub O, and then a liquid limit of 40. Okay. Okay. So to solve for part A, okay, then we need to get the average effective stress at the middle of the clay layer. No? Okay, so that means we need to get the average effective stress at the middle of the clay layer. So if this is the depth of the clay layer, then this is the middle. So that's about 1.75. No? That's one half of 3.5. So we need to get the average effective stress at that depth. Okay. So to do that, then the average effective stress, or that's your present effective. This is just the same as your present effective overburden pressure. Okay, or that's the average effective stress. So that's equal to 2 times the dry unit weight plus 4 meters times this. Take note, this is your submerged unit weight. No? Submerged unit weight. That's the saturated unit weight minus the unit weight of water. Okay, to determine the effective stress. Okay, you need the submerged unit weight. Okay, plus 3.5 over 2 because we need to calculate at the center. Okay, so that's the 3.5 over 2 again times the submerged unit weight of, in this case for clay, this one in terms of sand. Okay, so just substitute the values. We can get the present effective overburden pressure, sigma prime sub zero, is just the same as the average effective stress, okay, which is equal to this value now. Okay. So from equation 11.29, then we have this formula here, okay, wherein this we have already calculated this one here, that's 76. The initial void ratio is 0.8, okay, and then the stress increase is equal to 100 kilopascals. Okay, and then H is equal to that's the depth. Sorry, that's the depth of the clay layer, 3.5. Okay, and then this is now your compression index. Wherein in your book you have there some equation 11.33 in your book. The compression index can be related to the liquid limit, wherein the liquid limit is given as 40, and that gives you a value of 0.27. And then just substitute everything here, then you get a settlement of about 191.191 meters or 191 millimeters. Okay. Okay. Now, for part B, you are given a pre-consolidation pressure of 200 kilopascals. That means for part B and part C, we are dealing with over-consolidated clay. Okay, over-consolidated clay, wherein you have some pre-consolidation pressures. Okay, so then we try to check if the sum of the um, present effective overburden pressure or the average effective stress plus the increase in the effective stress uh, or the structural load bearing pressure, if the sum of that is less than or greater than the pre-consolidation pressure. Because if you recall, there are two formulas, no? Whether it is below the pre-consolidation pressure or above the pre-consolidation pressure. Okay. So in this case, we add now the average effective stress to the stress increase caused by the foundation. That's equal to 176, which is less than the pre-consolidation pressure. Then we can use this formula where C sub S is the swell index. Okay. So just substitute the values. Basically, it's just the same as part A. The only difference is C sub S because here we use C sub C. Here we use C sub S, where C sub S is the swell index, where the swell index is normally treated as, say, for example, in this case, 1/5 of the compression index. Okay. So one-fifth of the compression index, so basically the result here for the primary consolidation settlement will also be about one-fifth of this value here. So one-fifth of 191 is about 38 millimeters. Okay. Now, for part C, you're given a pre-consolidation pressure of 150 kilopascals. Okay. Now, if you compare the sum of the present effective overburden pressure or the average vertical stress, okay, plus the increase in stress or the load bearing pressure caused by the foundation, okay, if we compare the sum to the pre-consolidation pressure, then we see that the sum is now this time is now greater than the pre-consolidation pressure. Okay. So in such a case, then we can use the other equation, which is this one here. Okay. Um, to solve for the primary consolidation settlement. So then from there, we just simply substitute the values. The values we used in part A and part B, just substitute it in part C. Then we get a primary consolidation settlement of about 67.5 millimeters. Okay. Um, okay, so that means, yes. So that means if I want to get the total settlement now, then my total settlement can probably be, if there is no secondary consolidation settlement, then my total settlement is equal to the elastic settlement of 13.3 plus the primary consolidation settlement of either 191 millimeters or 38 millimeters or 67.5 millimeters, depending on the case, no? On the specific case condition. Okay. Now, either way, um, if my settlement criteria is 25 millimeters, then the sum of my immediate and consolidation settlement has already exceeded my settlement criteria if it is 25 millimeters, which is normally what we use in practice. Okay. So in that case, then we start to recommend ground improvement techniques, or we recommend deep foundations, such as um, board piles or micro piles or driven piles. But these are basically the formulas that we use in our calculations. Okay, I guess that's the end of my lecture. You were just on time. Apologies for that. Exceeded the time. So let me just stop share. Okay, so do you have any questions or clarifications so far? For the other problems, my colleagues can probably provide you that one, okay, for the other problems. So again, just to summarize, total settlement is equal to the immediate settlement plus plus the consolidation settlement, either primary or secondary. Okay, that's how we consider total settlement. And then in practice, we still consider liquefaction settlement, no? Wherein there's another way of calculating the liquefaction settlement. We either use Excel spreadsheets or we use commercial softwares to determine for that. Okay. Then we add it to the total settlement. So are there any questions so far or any clarifications that you want to clarify? Okay, so I understand that you will be having your um, um, pre-final exams, I think. Yeah. Okay. So you can just discuss with your with my colleagues for the topics on your pre-final exams. No? Okay. Yeah, I understand that is this week. Okay, so you can either have it this week or next week. It's up to you. Just discuss with your respective teachers. Okay, I'm checking the chat box. There seems to be no questions. So if there's none, then I think we can now adjourn. Thank you very much for your time, everyone.